Good day everyone, I am Frederic Salimi. This e-course will be uploaded in our training WORKSPACE. If you are interested in full access of this e-course, please send us an email given in description. Have a good day and talk to you later. A brief description about my qualification and experience. I have a master's degree in dependability, which covers safety, reliability, maintainability, and availability. I also have a BS degree in process control and instrumentation. I worked several years with engineering companies like Technip and operators like Total. I was involved in pre-project, FEED, detailed design, construction, and operation. Today we discuss about fixed fire water system. This is a generic version and will be customized for your project or for your installations. This course takes 1 day. We give you access to EPC 365 training monitor for discussions. The objective of this course is to give a practical understanding of fixed fire water system for oil and gas installations. Fixed fire water system composed of fire water pump, fire water tank, ring main isolation valves, and connections to the water consumers such as Deluge, monitors, hydrants, and the hose reels. Today we discuss about fire water pump discharge pressure, how we define this, jockey pump flow rate, fire water ring main, and fire water tank, and foam storage tank. Just to give a reminder here that the isolation valve they have to be configured in such a way N-1 that in case of the maintenance of any branch, the fire water system should be available. Capacity. We discuss about deluge monitors and maximum fire water demand. Here, if you see here is a typical deluge system here. Here you have your ring main here, and also here ring main, and here you have an automatic deluge system, and and here is manual. Normally it is upwind. In case of the fire detection, this valve will open and will give the fire water deluge system for the equipment of the protection. I give you a little explanation about the deluge system, how it is deluge system. This is a deluge system. Normally it is by the push button or by fire and gas. We release the solenoid valve, and then this will open the water and goes to the system. So normally we have locked open valve, and also you should remember that deluge valve is a fail open system, and in case of the test we go it for the this line can go to open the system, can go overboard in offshore. So this is the deluge system, typical that we call it here. There are certain installations we put to the deluge system and not manual, but this deluge valve skid normally should be at least 15 meters from the protected area to be safe. So there are certain things about the configuration, how it will be working, and we will discuss it in our workshop when we see each other. So about a brief description about code and standards. Normally NFPA 13 is for sprinkler system. We don't discuss it in this e-course. There will be another e-course. NFPA 15 for fixed water spray system, Deluge, and 1620Y. IEC 60331 and 332, and ISO 13702. So selection of deluge equipment. Normally in the installation there are the company guides or the code and standards. For example, here offshore and onshore, you see, for example, for wellhead, in offshore you have to put deluge, and in both cases for onshore and offshore, for all the vessel that contain hydrocarbon or pump, heat exchanger or column, should be deluged. A slug catcher is for onshore, etc. So the criteria for the deluge is normally by the liquid hydrocarbon liquid inventory. If it is greater than 5 cubic meter, normally you will deluge the equipment. Deluge requirements shall also be installed regardless of liquid inventory if mobile firefighting means are not quickly available or of sufficient capacity, or unit layout does not allow for efficient use of fire monitors. Deluge shall be installed on large units if the pressure and multiplied by volume more than 3,000 bar cubic meter. And again, monitors are adequate for a smaller unit. Deluge shall be limited to equipment extremity and 5 meter beyond. And deluge for tanks larger than 1,000 cubic meter. For a smaller tank, decision is to install deluge shall be governed by availability and capacity of other fixed or mobile firefighting system. So when you decide to put the deluge system in an equipment in vessel, normally application rate is as per NFPA is 10.2 liter per minute per square meter. For the pump is 20.4 and etc. And as I said, is based on NFPA 15 and ISO 13702. And fire source shall be investigated to confirm that equipment structure above 12.2 meter are not impacted by effect of fires. Manual firefighting means shall be provided in the vicinity to enable firefighters to cover higher part of the concert equipment. Deluge for wells shall be by means of high velocity spray nozzles. For condensate storage, application rate shall be based on 2.5 liter per minute per square meter. And finally, bond area for condensate storage will have a phone system directly inside the bond, and it will be based on 2.5 liter per minute per square meter. So now I show you how we can do the fire water demand calculation and foam demand. So this is a typical example of an installation, and now I want to show you in fire zone 1. If there is a fire here, the ESD valve will be closed and deluge will be released as per cause and effect matrix. The same things for here. So this is a fire zone 1. In this project, we put deluge for a slug catcher, a slug separator, manifold, and MRU, including 20% contingency. And for the fire zone 2, because it is too big, and we divided to sub deluge zone A and B, and this is because the fire zone is based on the not only thermal radiation but also LEL, explosion over pressure. But if you look at the very well about the thermal radiation and criteria for escalation, you can divide the installation in sub-deluge zone, and you have to be careful about sub-deluge zone because it will help not to oversize the fire water pump. So this is a typical example of the fire water and foam demand calculation, and basically in this calculation sheet it is written, for example, in separation and trunk line arrival, MRU, and pipe rack and structure. So all of these things with the tag number, you have to say, okay, if it is horizontal or vertical, and will it have contain hydrocarbon, and if it is flammable combustible, for example here no, and if it is flammable, the capacity, if it is more than 5 cubic meter, here yes, no. And then you have to put a note here for auditability and traceability. For example, no deluge because protected by monitor this big launch book receiver. For example, it here for a structure not deluge, and we have to write why. And does it have PFV? Does it have any other protection? For example, here not provided PFV only for example this pipe rack. So when you decide that you put yes, you have to deluge, then you have to define the dimension about height, length, and width, and then finally surface, then application rate as per NFPA, and then minimum fire water flow rate, application rate by surface. And then when you have this, and then you require of the foam, if it is 3% triple F, then you can calculate by this, and then actual what is required, then you plus contingency, you come with some flow rate here. And for any installation, this is the criteria of the company, that you have to allocate 60 cubic meter per hour for an hydrant, and 120 for monitor, basically 200 cubic meter per hour you add to the deluge, and you come up with 574 for and this requirement of the foam for this fire zone 1. So the same calculation has been done for different fire zone, for example, fire zone subdeluge A and B, and this one, and basically this one is the higher water demand, and this is the foam capacity, and based on this, 2 fire water pump diesel was provided. According to NFPA, there should be different for the diversity, one electrical or one diesel, or 350% one motor and 2 the diesel. But in this case, because of the reliability and availability of the fire water pump company, for this project company accepted that we have 2 diesel fire pump. So then we discuss about the discharge pressure later, based on the capacity of the based on the NFPA 20, the required capacity of the fire water pump is 682 for this project. So about the fire water tank, certain project they get 6 hours, but you have to be very careful that 12 hours is for the local authority, and local authority normally it asks for 12 hours as far as I know. So if you put 50%, you can calculate the capacity of fire water tank. For the jockey pump, normally jockey pump is for pressurization of the system. Normally we take it to 100% and about 60 cubic meter per hour. And fire water ring main based on the maximum water velocity of 3 meter per second. We can define with this flow rate, maximum flow rate, the diameter of the fire water ring main, and based on the type of the if it is GRE or if it is steel piping, we can define the selected design pressure for the ring main that should never exceed 13.9 at 90 degree. So this is based on the material class of the fire water ring main. Now discussing about the deluge valve, normally for the deluge, as I said, we have to have two sets, and remember that the fire water system, according to NFPA, should be 100% available. Is it the same for the ring main, fire water pump, and the deluge valves? And for this project, for different branches, it became as a 8-inch for the valves. And if you see here for the fire zone number 1, we had the deluge system with the capacity it become 8. First is A and B, and then it was 2 automatic deluge valves. If A doesn't work, B works. For fire zone 2 sub deluge, the same things, and another sub deluge B, but all of them, they have to have 2 automatic deluge valve, as I said, 15 meter from as far as possible from the source of the protected area. From a storage tank, normally the capacity is based on 20 minutes operation at maximum demand, and plus for the 20 minutes reserve supply. And here it shows that in fire zone 1 for deluge foam system we require 8 cubic meter foam, and foam shall also to be provided for the foam tanks to feed the monitors and hydrants. And for the hydrant and hydrants, we put it at the foam tank capacity for this project was 600 liter. At the end of this presentation, I gave a video from a vendor, and it shows how to generate foam for the fire protection system. So this is a typical deluge valve skid. As I said here, this is a deluge valve. Here there's a Venturi, this is a deluge foam tank, and this is the test line, and it goes to the system. And this is here by the, as I said, is from technical building, from fire and gas, or from push button. This will be deluge skid for the deluge foam skid. But sometimes if the deluge is only for the cooling, so there is no need for this one. So as a conclusion is in order to calculate the discharge of the fire water pump, we have to look at the distances of the fire water pump to the furthest distance to the monitor. For in this case, in this project was 760 meter. So pressure required at further monitor is 7 bar minimum. Pressure drop through the firework network, it was calculated based on Hasan-Williams pressure drop calculation 1.5, and operating pressure, so 8.5 plus 1 at elevation of 1 meter, and fire water discharge pressure should be 8.5 bar gauge at 576 cubic meter per hour for 12-inch ring main diameter. And jockey pump for this project should be 8.5 bar gauge at 60 cubic meter per hour. Now I show you about this training workspace. It is in safety engineering training in active fire protection. When you are in active fire protection, if you want a customized training, clients should put all the documentation about active fire protection. Then we create an e-course. This e-course will be subject to approval of the company. When it is approved, the employee can go in this discussion here, and they ask the question, and we will answer to their questions by our experts. Thank you very much for your attention. If you have any question, please send an email to pmc@epc365.com. We have two websites. One is French, one is in English. There are request forms there. You can ask questions. We will get back to you as soon as possible. Have a good day, and talk to you in our next workshop.
Offshore and onshore operations involving hydrocarbons and other hazardous products always face the risk of fire. Adequate protection measurements are of vital importance to avoid large-scale environmental impact and devastating loss. One of the most effective ways of fighting fires in the industry is using foam systems. These foam systems depend on special equipment to guarantee the correct foam-to-water mixture rate. This can include foam pumps, which traditionally come with some challenges. Most foam pumps need power, either high-voltage electrical power or diesel engine-driven, both expensive to install in hazardous environments. Other pumps may be driven using a water turbine, but these have huge loss of precious water. In an ideal world, such a foam pump would operate at zero water loss, zero power consumption, and low noise, yet providing the most accurate mixing rate regardless the foam concentrate, and fully immune to dry running, overspeed, or corrosion. An innovative next-generation foam proportioning device that is driven completely by the flow of water, requiring no additional power supply. Available in 3 sizes, 4-inch MIDI, 6-inch MIDI Plus, and 8-inch Maxi, the Turbinator has a flow range of 500 to 12,000 liters per minute, suiting most applications. The Turbinator is basically maintenance-free and has no water consumption, so all water will be used for its main purpose, extinguishing the fire. All of this resulting in high reliability and cost savings at both CapEx and OpEx stages. The Turbinator can be incorporated into any existing type of foam firefighting system onshore or offshore, whether in storage tank farms, for bund areas, tank protection with foam pourers, deluge protection of process plant, or in jetty foam systems including Knowsley tower-mounted remote-controlled monitor systems. The Turbinator comprises 2 main items closely coupled into a single unit. These are a water motor and a foam pump. The water motor is driven by the system water supply, and all water carries on to the system, so there is no wastage. The foam pump is on the same twin-shaft arrangement as the water motor and rotates at the same speed. A strong suction is created in the foam pump, which sucks foam concentrate from any available source, without the need for priming. The volume of the water motor and foam pump are directly related, with the foam pump being either 1% or 3% of the water motor. Each full revolution of the water pump moves a fixed volume of water from the inlet to the outlet. At the same time, because the foam pump is on the same shafts, it sucks foam at a related fixed volume and pushes that through a port in the body into the water stream at the outlet side. This results in a 100% accurate mix of foam solution, regardless of any outside influence. In other words, the Turbinator is a positive displacement device. A 3-way valve is fitted in the foam suction piping. In normal use, this allows the foam suction to take foam from the tank. However, it serves a dual purpose, as it can be set to isolate the tank and allow water to enter from the inlet of the Turbinator, thereby allowing either a flushing action or to use water for testing purposes instead of foam. By design, the Turbinator is highly flexible and effective, even in the event of simultaneous demand from different applications at the very same time. The proportional creation of foam will adapt automatically to the current demand in real time. The Turbinator has already successfully been implemented at various high-risk sites, saving cost on energy and maintenance and offering higher reliability. If your situation requires a foam pump installation that needs no power supply and virtually no maintenance, while offering zero water waste and 100% correct foam proportioning, then the Turbinator is the answer.